So thank you very much. Thanks for having us here. My name is Mikkel, and I work at Fermyon, where I lead our developer relationship and product teams. Someone is part of our developer relationship teams as well. We're a company that are a bit more than a year. No, that's not true. Almost 2 years old. When we get to November, the company is 2 years old. We're a company that is basically worldwide. We used to have people on 5 continents. I think we're down to 4 now. But 9 different time zones at least is how we're spread, with around 30 employees at this point. And the company was founded by 2 of my previous colleagues, who are now colleagues again at Microsoft, basically on the vision of pioneering this next wave of cloud computing, as the tagline is, which is WebAssembly. So, I mean, what I will do is spend the next time in this talk presenting to you is I'll basically show you a framework we built that is called Spin. That is a framework to build serverless types of applications, and that is built using Rust and uses WebAssembly heavily as a core component of how the whole framework works. So you can sort of dive into different things during the talk. Hopefully, you can look at this as an opportunity to write Rust code, because you can write Rust code using this framework, but also be more interested in the framework itself, which is also written in Rust. It's an open source framework, which means contributions are always welcome. So if you want to go to a place where you can apply some of your Rust skills, this is definitely an opportunity to do that as well. Okay, with that being said, I'm just going to try and show you Spin to begin with. We'll spend some time with that, and then we can go a little bit more into a talk later of, what's the whole WebAssembly thing as part of this. We might want to do that as we go along with the experience as such. And if you have any questions along the way, just raise the hand. I think we are, like, the crowd isn't bigger than we can just take questions as we go along the way. Okay, so what I have on my laptop here is this thing called Spin. Spin is version 1.41 today. And all I had to do to get started with Spin is, download this installer. I have done homebrew here on my Mac machine, but we have installer scripts as well. And then obviously I need whatever language I want to use with Spin, I need some tool chains for that, right? If I want to write some Rust, I need a Rust tool chain. If I want to write some JavaScript or TypeScript, I need some of those, Python, whatever language I want to use. But the way that I can get started with Spin is that I can start by creating a Spin application using a Spin new command. And for not to make myself too confused, let's just call this Rust Meetup. So what I have as I'm getting started here is, let me just do that, is a small TOML file that's a description of the application I will create. There's some stuff that I did up here. I'll get back to that later, the HTTP entry, what that means and all of that. Actually, I can start doing that right now. So Spin, as I said, is a serverless framework, which means that the way that you build applications with Spin is you build these small components. We call them Spin components. And each Spin component, you can consider that somewhat of a function, right? That can be a self-contained function that is executed based on some triggering happening. There's a bunch of different triggers you can use. The most widespread one is using just HTTP requests. So whenever an HTTP request hits an endpoint, that will be a trigger for a function to run. There could be a trigger monitoring a Redis queue. So things happening on a Redis queue will trigger that function to run. And basically the whole trigger system in Spin is pluggable. So there are a few, the ones that we build is the Redis and the HTTP one. There are a few triggers that have been built by other people who contributed. Looking at MQTT, I think is one of those that have come in recently, and there are others out there as well. So what I'm doing when I'm doing this add command is I'm basically adding a new component to my Spin application. And we sort of have this notion of, trigger / programming language that I'm going to use. So in this case, I am going to add a component that is HTTPS triggered and that uses Rust, and I'm just going to name this run Rust. As I go ahead and do that, you can see I'm being asked some questions around HTTP path. So what you should think about here is when I build a Spin component or a Spin application that has a bunch of components in, right? And they might all of those be HTTP triggers, some might be other triggers. they each listen on the same endpoint, but there are various paths that they serve, right? So you can imagine how you can build out these applications where slash Rust, for instance, which is the one that we can create here, is going to be served by this one component, but then there would be a slash something else that'll be served by another component, right? So you can sort of, construct applications by having these small pieces of code, or having these components in there that sort of make up the application. Okay, so going into this Rust thingy that was now created, you can see we have actually a Rust library that is being built in here, which means there's a cargo TOML file where I can do the dependencies and all of that I need. And then we have a lib.rs file, which is our sort of what we get with this template that we've used here, the Rust HTTP Rust one. So a few things that you know in here is that we have an SDK that comes with Spin, and that SDK implements a lot of different features that we will use as we write out this function. One of them is that we have this HTTP component macro or whatever that we added in here, so that we have decorated our handler function to tell the Spin framework that whenever this component is triggered, this is the function that you should pass in the request to, and whatever the request is what we're gonna pass in here. So I can add whatever other function I need in here, but there will be one that we need to decorate at the component to make sure that the framework knows where is the actually gonna deliver the request in here. So this is fairly simple, right? A request is being handed over to our function. We're gonna return a result containing a response here, and basically we're just printing out a few information and then sending back an HTTP response. So if we just want to look at how that looks, let's go in, and I think I'm going to forget along the way what I called it, but this is going to be called Rust Meetup. Okay, so what I can do is I can run a command called spin-up. I can't run spin-up right now. I can run spin build to begin with. And basically what spin build will do, it'll actually read our config file from Spin, the Spin TOML file. I'll show you that in a little bit. And that will help, in that file, I can define how these individual components are being built. So basically what this is doing right now is just doing a cargo build and creating the executable, the binary that is behind this component. So now if I do a spin up command, we can see that we get an endpoint where this component is at. And if I go over here and we just curl that, hello Fermyon. Okay, that's pretty straightforward, right? We have an HTTP function that returns something based on the request that's being sent in.
You're silently defaulting to get method?
I am silently defaulting to get method. I'm not doing anything up here to evaluate the request in the code that I have. Let me move this down a little bit, which means whatever request comes in is being handled by this code.
Okay.
So there's nothing in my code, trying to figure out whether this is a get or put or whatever it is and doing that. But that's actually what I'm going to show you right now.
Oh, sorry.
No, that's absolutely fine. Okay, so that was fairly straightforward. I have a lot of code that I'm going to copy in along the way because you don't want to see me try to write all this as we go along. So let me go over here and add a few snippets. So the first thing I'm going to do is that I will go up here and actually I'll go over here and I'll add in another component from the SDK, which is an HTTP router. So that, sort of along the line of what you're asking for, we actually have a macro that we built into the SDK that helps us route the request based on method types or even sort of patterns of whatever the UI is for what's being put in here. So let me just go over and take my code here, and I'm gonna delete a bunch of stuff. Let me delete that, and now I am missing a closing bracket, and then we're just gonna paste this in. Oops, and I'm used to a different keyboard back home, so what am I gonna do here? Oh, I don't need this closing. Let me get rid of that one again. Okay, there you go. So what I did is I took that HTTP router macro that we have, and you can see now I can easily go and sort of set out some logic in terms of, or evaluate the request, where I'm saying if I get a get request, of this pattern, I'm going to hand that over to a function called getStuff. In post, I'm going to hand that over to a function called setStuff, and then I have some default response here saying, I'm not going to be able to handle whatever you gave me now. So that's also an option that I have. So once I have that in, let's go and just put those two functions in there. And what I'm going to do in those functions is that, having a framework like this, a serverless framework, I guess the things that come closest to what this is something like AWS Lambda, or something like Azure Functions, which some of you may know of. But the type of stateless execution that we have here, and we should also get back to that, because what's interesting about these functions is that they are loaded on each request, right? So between requests, we don't have any place to persist any type of information that we want. So what we would do is we would need some kind of persistent storage outside of this component, which is where we build in some features to the framework to use sort of a generic key value store. So basically a place where we can add in, a key and a value in some data, but also using SQL by SQLite implementation. So what I'm going to do right now is I'm going to add some function here, these two functions, getStuff and setStuff, to actually use that key value store so that I can start persisting data between my requests. So the first thing that I'm going to need is I'm going to need a few more imports up here. Oh, I was already there. So I'm going to add some key value features from the SDK. And then I have a few functions down here. I have a set and I have a get function. I'm just going to put them all in now, and then we can go back and look at what's actually happening there. Just want to make sure that everything looks okay. Okay. Did I put too much in? Or what's happening? Let me see. There's something. Oh, I didn't get params up here. Let me add that one. I just need another. Whoops. Okay, that should be it. Okay, so what I did in these two functions now is, so setStuff, we get the request through the router and some parameters that we put down here. I want to use my key value store, so basically there's a store.openDefault, that will give me a key value store. I take out the ID from the parameter that's being passed that is part of my URI, and then I can go and check, in the store if that key actually exists. I'm just going to print out whether it exists or not. And whether it exists or not, I'm just going to override it, right? Okay, this is demoware, right? So just take for what it is. But you can see there are some simple APIs here to basically work with that store and have some data persisted in there. And if you take a look at the get, I'm sort of the same pattern again. I'm opening the store, I'm getting the ID. I'm going to check, get the store, and if it's there, I'm going to, return the value back. If it's not there, I'm either not finding it, so there's no such key arrow, or or there's just a generic arrow with like the worst HTTP error in the world, which is 500, meaning you can't do nothing, and that's is what we're going to return. So with all of that put together, we actually now have a function where we can start persisting data in a key value structure. There's one more thing that I need to do to get this up and running, and I think this is where we can talk a little bit about this spin file. So spin.toml, as I said, is defining what a spin application looks like. So there's a little bit of metadata at the beginning you can see for the actual application. You would notice that the trigger is part of the app manifest metadata, which means that actually today in an application you can only use a single trigger type within one app. Like there's some work we have experimenting with and being able to mix and match trigger types, but that's sort of a requirement today. But then what you have, sorry, yeah.
Do you have some other examples of types that go into trigger out of an HTTP?
So a Redis queue is one of those that we have. That's the one that we built. And then there are at least 2 or 3 examples out there that other people does. MQTT, I think someone did an SQS trigger as well. And there's been some experimentation around so like a cron type of trigger, like a time-based trigger, right? So those would be examples. But again, it's an extensible thing, so you could build your own trigger into the framework if you wanted to. So what I have done here is then this is end up being an array of multiple components from my application, right? So I have the first component, which we call Rust. There's a WebAssembly in here. Finally, there's a WebAssembly, right? The actual source that is behind this component is just a WebAssembly. And we can expand on this a little bit later what that means, and I'll show you an example of how that actually applies here. But basically, the combined configuration here means that for this application, anything hitting a Rust/Rust endpoint are going to be served by this WebAssembly component. And then you can see there's some build stuff down here that I mentioned early on. If you run that spin build command, this is how you can sort of interact with how you build pipelines. It's going to be set up for the individual components. So the thing that I need to do here is that I need to allow this component to get access to key value. So I can add in key value stores, and we have this beautiful experience of a default key value store. So what you would do is that you'll basically for each component that you add in here, you'll define which key value stores would be accessible for that component. The same way you can see if you want to do outbound HTTP requests, you need to define for the component which host is the component allowed to call. And you can add more key value stores if you want. And what's even more interesting is that these key value stores can be shared between components, right? So they can actually work against the same data store. So there's sort of flexibility in how you need to structure this and what data is owned by which component. So let's try and go back, and I'm going to do this now. I'm going to run a spin watch command instead. So spin watch is this nice little command we have where for these components, you can see I can define a certain set of files or a blob, what do you call it? This type of search pattern, where there are certain files that are being watched for changes, right? So actually, as long as my spin watch command is running down here, as a developer experience, as I keep, changing my file and saving it, it'll just continuously recompile, so I don't have to go back and do stuff there myself. But what we should be able to see now, if we go back and call our service, we can add some data in there. So let's maybe do a post, and the way that the signature works for the service story down here is that I had to decide my ID in the URI path, and then the data is basically just going to be the value. So we can go and put that data in. We got a 200 pack, and we can see that we were storing that key. And if we go back and we'll just go and ask for a particular key, we got the data back. And there's really no, we can do what we want to do with the key here. I didn't implement any, any type of, any rules or anything about the key, right? So it could be a string. It is basically a string, right? But I could put in some string. I could put in whatever I can fit into that string. And the key, the value in there is just a blob that we end up storing. So again, you can put whatever you want into that blob.
I noticed for the key value store and the HTTP routing, you don't mention the technology. Is that because it's like an in-house key value store, an in-house web router?
So the router that I've used in my component is a macro that we've written in Spin. So that's part of the SDK. So you can find the macro implementation as part of the SDK, and all of that is open sourced. I mean, there's as these WebAssembly components run, there's host underneath, right? When I run spin watch or spin up over here, I actually start an executable, which is, we call it the spin host runtime. That implements the web server, right? Because I need a web server. So that sits in that host down there, and that's the one who's actually listening to the socket that I will open, and that has the information from the component of where to route inbound requests. So there is a web server implemented there, and I believe we're using Hyper inside of Rust. Inside of Spin in that scenario. But if you want to dive into that, you can go and check out the source.
Yeah, I guess my question is from an ideology point of view.
From an what, sorry?
From a point of view, the Spin framework is the idea you just have a key value and you're trying to abstract away deciding what the tech is.
Yes, so the key value store is, again, the way that it's built, the features built into the framework is pluggable. We try to do that with most of the stuff. So what sort of the developer experience, right, that we built here, you can see I have in my directory down here hope everyone over there can see over there. We've actually built this using SQLite. So we run a local SQLite version, and I think if I went and dumped whatever was in there, you would see a table called key value store that had like, a key and a blob, something like that.
And then if you wanted to use another form, you'd create an adapter or whatever the terminology was for the framework.
So you can build, so up here in the key value stores, default is sort of a magic word in that it's a convenience feature, we can call it, right, for this developer experience where you don't have to think about getting a key value store somewhere to just do your development, right? So you just add in default, we give you the SQLite thing that we've implemented, and that just works, right? You don't have to do anything.
Okay.
What you can add to your Spin application, you can add this concept of a runtime config, which basically means that you could have, my key value store or other stores over here, and then your runtime configuration will point to a key value storage implementation that could be Redis. So you could run a Redis somewhere, which you would then use. And I think we have an implementation for Azure Cosmos DB. There are a few implementations. We at least have the Redis implementation.
Okay.
So
and then last question.
Yes.
So, whether you change that, the API for like the function will be the same.
Yes.
Setting and getting keys, like that won't change.
Yeah, the only thing I'm doing as I sorry, I'm keep using my mouse here. As I'm opening you see I'm using sort of that the magic default here, right? I could do an open bracket and then the name of the key value store that is specified in that spin.toml file, and that will then point to, and then you get to your Redis or whatever it is.
Cool, thank you.
Cool. Okay, that was sort of, you kind of get the idea of how this works, right? I could write these functions and I can start building out my applications this way. Let's try and add some more stuff in here. So we have this concept of templates. So really, when you think about Spin, there's actually like 1,000 things going on, right? There's a CLI, as you can see. There's that core runtime. There's this concept of components. There's key values. There's a bunch of stuff. We also have a templating system. And what these templates give me is that they are basically, when I run the spin new command, I'm able to use sort of, pre-packaged templates that, can give me like a spin.toml with some information in and some code that is being scaffolded for me, right? How templates work and these type of things. And there's a whole bunch of stuff that we built here and that we sort of provide out of the box. So, you can start to get an idea of the coverage of programming languages that are supported. I would say not every HTTP is equal. It's the same. There are two ways of doing that communication between the host and the component. To sort of shortcut that whole conversation, some languages we do have SDKs for, some languages we don't have SDKs for. So that's probably the easiest way to think about it. We do have SDK for Go, JavaScript, TypeScript, Python, Rust, and some very experimental C# stuff. Those are the languages where we do have SDKs. So the fancy stuff of key value, and I'm going to show you hopefully SQL and other stuff, you will find them there. If you use things like Rain or C, or I think there's even SIG in here and things like that, you don't get an SDK at this point. But there are other things in here we can use. You can see that because a lot of the benefits that, anyways, so one of the backgrounds of all of this and this whole project is that I think the core of what our company is really about and what we want to achieve here is just like, to make, it may sound a little bit trivial, but to make it developers' lives better, right? Like it just has to be easy, right? And we fully believe that, sort of a serverless way of writing applications is the better way because, you don't have to think about dependencies in terms of infrastructure and all of these things, right? We just talked about how I don't need let's say if what a lot of people do today is container-based type of development, I don't need a Redis container running to get some key values to open, right? I can just write some code and use those APIs like store get, store set, store exist, let's key, whatever. I don't have to think about this other thing, right? And I think that's sort of where we think there's a big difference in what we can do developer experience-wise and productivity-wise compared to, for instance, containers. And one of the big things that enables this is WebAssembly. Because under the hood, these things, and I showed that up here in the spin.toml file, that the Rust code that I've written here is being compiled down to WebAssembly. If I'm just going to go back here, you can see that the build command that we use is using this target called wasm32wasi. WASI is the WebAssembly system interface. And the WebAssembly system interface is sort of the new twin. That's not a thing. I know it's not a twin thing, but it's the new twin to what WebAssembly in the browser is, right? Because WebAssembly was originally specified as a standard for running applications inside of the browser, where you could use other programming languages to talk through the browser APIs, through some JavaScript glue code and stuff like that, right? So you may have heard these stories about how a company like Figma and Adobe have built very quick performing and feature-rich experiences in the browser by using WebAssembly and having written a lot of the browser experiences in languages like C, for instance. So if you think about that, WebAssembly comes from this world of the browser, right? There are a few things that just have two priorities when you design something for the browser. First of all, you have to have a binary format that can be run across platforms, right? Operating systems and processing architectures and all of that. So that's a core design criteria. Another core design criteria is that binaries have to be small, because you never execute a program from your local disk. You always execute a program by downloading it over the network, and then once it's in your browser, you can start executing, right? So there's another core design principle there. It has to be really, really secure, because everything you run is untrusted. Like, you have no idea. Well, you actually have no idea where it comes from. You might think you know, but you don't. Which means that everything has to be run in a very secure sandbox. So this idea of in WebAssembly, we talk about it as a capability-based security model, meaning that the capabilities that a WebAssembly component need has to be defined by whoever runs it. So for instance, if my component needs access externally over HTTP, I have to define it here. If it needs access to the value store, I have to define it here. If it needs access to files, like static assets, I have to define it here. If that's not defined, you can't get to anything, right? So that's another core design principle in browser. And the fourth one is the startup time. Like, things have to start really, really fast, because again, in the browser, you need to download and then you need to start and so on and so forth. Like, what WASI is taking those design principles of WebAssembly and bringing them outside of the browser. So now you have a system interface, which means that you get access to file systems and other things that you don't have access to in the browser, which means that we can build WebAssembly that can run in WebAssembly runtimes outside of the browser. So typically inside the browser, you will run in things like V8 or SpiderMonkey. Those will actually be the WebAssembly runtime implementations inside of the browser. Outside of the browser, we have things like Wasmtime, which is the runtime that we're using. Wasmtime is built by an alliance called the Bytecode Alliance, which we are also heavily involved in together with other. But there are other WebAssembly or WASI-compatible runtimes out there. So what we've done with Spin is we've taken that WebAssembly runtime and built it into our core host. So basically, the way that this thing ends up working is my Rust code is compiled to a WASI target, which means I get a WebAssembly. Once I get to the point of having a WebAssembly, we actually don't know where it came from. Like, in this case, it came from Rust. It could have come from TypeScript. It could have come from one of these other languages. But at this point, it's the same specification that it's compiled down to. So what we do when you run the spin command here is we set up that host, we enable those triggers that are defined, and then basically Spin has this mapping of any HTTP call going in here is served by this WebAssembly, and that's all Spin knows. So whenever a request comes in, the Wasmtime runtime inside of Spin sets up, I think it's called a store in Wasmtime, but basically it sets up that virtual machine loads that WebAssembly inside of that virtual machine, handles the request, and unloads it again. And it sounds like a lot of things that have to happen, but if you go back and think about those core principles of, small binary sizes and quick startup times, you actually can't see it from when I'm running a request that all of that, this thing has to happen by just handing that single request. And that sort of takes us to that thing about a serverless model, right? Because if I had like 10 components in here, I wouldn't have, scaling doesn't become a thing in this case. I know eventually my CPU can handle what my CPU can handle, but I don't have to, I don't have to have an operations practice around how many do I run of these. Do I want to scale them up? Do I want to scale them down? If there's 1,000 requests coming in a second, this thing will be loaded 1,000 times and handling those requests, and that's it, right? And these things can happen in parallel in the host runtime. How that works. So I hope that gave you a little bit of sort of how does WebAssembly fit into this, and the type of experience that we built here. Yeah, that was a long talk. Any questions on what I said? Yeah.
Yeah, I actually have a question. You mentioned that like 10,000 requests that come to the service, and it will be downloaded 10,000 times.
It will be loaded.
Loaded.
Yeah.
In the client browser, or.
So all of this runs on my machine here, right?
Yeah.
So the way that Runtime is set up, as it's when I run the spin command, I think I actually might have a slide here. I did some slides actually, but we're probably not going to use them. But I do have something. Let me see. I actually have a lot of slides. I think I have one that's trying to explain this whole. Well, get rid of clunky containers. There you go. This one. So what happens when I run this spin up command, right? Spin is an executable I have on my machine. Is it actually runs another command called spin trigger, which then tells, because of the TOML file that I had, that I need to now run an HTTP triggered spin application. So this is a child process of the parent process up here, right? That one has like this mapping that there are multiple components in here that could be served. So the HTTP endpoint sits in the parent process up here, right? And that also knows when to route down there. So when an HTTP request comes in, or Redis trigger, or something comes in, this error is wrong because it actually goes up here. The request or whatever comes in through the trigger, whatever data comes in, is then being routed to the trigger. And based on the mapping on the individual component, that Runtime thing is being loaded inside of this process, loading the component, handling the request or the trigger message, and sending the response back. And after the response has been sent back, this part is being unloaded again. So that is not part of this child process anymore. Which means that, one of the things we talk about in this whole serverless thing that we built is that, if you've ever dealt with Lambda, one of these services, there's a thing called cold starts, right? And there's a good reason why there is that those cloud services, but in this case, we don't have cold starts. I'm actually just going to try and show you one thing. I haven't done this in a long time, but to just prove a point, this is Slack. This is our company Slack. I have I'm not sure if my app is still running. So before I go there, by the way, I can run all these things locally. We've also built a cloud because everyone wants a cloud. So we have a thing called Fermion Cloud. So I know I'm not going to get through all of my demo with this, but the next thing I could do in the workflow that I'm in is basically just call a deploy command, and that will wrap up the whole thing, and you now have it in the cloud. Let me just do that, and then you can actually see that is working.
Out of curiosity, would we have it in a cloud or your cloud?
My cloud. It's not your cloud.
You can self-host it.
You can self-host. You can host it anywhere, right? I mean, you can have spin being run in. You're gonna run spin in a container if you want. A lot of people want to do that
For no reason.
because they have containers. Anyways, there you go. Now my application is actually running in the cloud, and I think it's ready in a second. It should be ready.
DNS.
It's probably the network. It's always the network. Or DNS or something, yeah.
Yeah.
Anyways. Oh, you know what? We didn't... that's actually my app, right? Yeah. I get whatever. That was actually my fault. So yeah, I didn't put in a key, so I asked for a key and the key is not found.
Did you just deploy it in the cloud or what?
I just deployed it in the cloud or what?
Yeah.
I mean, developer experience, right? This is nice. This is so easy. Like, there's nothing. It's just like, oh, okay, there it is. And I can actually go into my cloud and I can add some custom domains. I can bring my own domain, whatever. You get 5 apps for free. You get 1 million requests a month, something like that. I don't know if it's 1 million, but you get a lot of stuff for free up there. All we ask for is a GitHub username, and that's the way you sign in. But again, yeah, you can self-host this whole thing, right? So you can just take the CLI and put it in a container. But because the way that the Spin framework is built, you can take all the core crates that are needed to understand the app model and the host system and build your own host implementation. One of my colleagues did a talk recently where he built his own host implementation. So, pull it apart, put it together the way you want, whatever fits your need. But going back to that cloud thing, let me actually show you something. This may or may not. Okay, this is going to go off script, so there's a high chance of this not. I have a bunch of apps in here. You can see I'm in the cloud. I have this app. This app was created a while back. When was the last time I used this app? I used this app July 5th. Okay. So basically, and I'm not sure if it works, that's right. So basically this app is just a webhook, right? So whenever I write some message in Slack, there's a webhook being called into this app and the reply is going to come back. This app has not been running since the beginning of July. I just want to highlight that, and then I want to see if I can... So talking about cold starts. See, this is the last time I did this. July 5th. What happens when I press enter is the webhook from Slack is going to call into that. Our cloud thingy needs to find the component, send a response back. Oh, God damn it. But there you have it. The response is already here. So no cold start. This application has not run for almost a month. Now I'm also getting all excited. But this is what we can do with WebAssembly. Obviously, the way that we build our cloud, which is multi-tenant and all of those things, is a different host implementation than what you get in Spin CLI, because that's our secret sauce, and hopefully we can make some money once all the funding runs out. So it's not exactly what you see in Spin, but those are sort of the things that go together there. Okay, I got so much off script right now. I have no idea what I'm going to do next, but I think there's one thing I want to show you actually. So again, developer experience, for me, that's the thing. So we talk about these things as components, right? We built that Rust component already, and I was showing you the templates, right? Now, because these are WebAssemblies, I can actually pull in any random WebAssembly binary that implements the interfaces that the Spin host requires, right? And what I mean by that is that you saw we had that annotation, the HTTP component annotation on our function in Rust all the way back. That is part of that interface. So if someone built a WebAssembly implementing that interface in random language X or Y, I can make that part of my application. So we have this thing called the KV Explorer in here, which is just a web UI to see what I added into that key value store. So what I can do is I can go and add that to my application using a Spin add command. I'll just do just means that I'm going to accept whatever defaults that would be in the template down here. And now I have that component. So now I can go back, run Spin up. I already had this component locally cached on my machine, but otherwise it would have downloaded the WebAssembly, but just the WebAssembly, which is probably a few megabytes. But what you can see now is I have another endpoint that I can call. So we can try that. So this thing implements security, like basic authentication. I don't know if that's security, but anyways. So it just gives me some credentials I'm gonna add in here. But really the main thing that I wanted to show is how you can sort of get to, so you can see this is the data that we added into that key value store before, right? So you can see this with one, hello one, and this other one. The credentials one is the one that it's creating itself. But you can sort of hopefully get this idea that you can start composing applications, right? Like you can have certain components that, like for this one, gives you a UI to manage the data you put into the key value store. This would also have worked if I had implemented my key value store using Redis, right? Because it's just going through the Spin API, which takes care of the whole thing under the hood. And I think I'm going to use the last 3 minutes to sort of tease a little bit of the future in that direction now that we're talking about components. Because in the world of WebAssembly, this is going to be a slide thing because I don't think I have anything to... I think I said most of the stuff in here by now. Oh, I want to show you this is a fun one. I'm comparing a Docker file that implements a Python Flask API and then implements a WebAssembly written in Python that does the same thing as the Flask API. And actually, these are the actual size comparison, like I measured on the slide. So just to give you an idea, when we talk about this as being the next way beyond containers, we can put our Spin WebAssembly in a container that is 550 kilobytes, as opposed to a Flask container that is 23 megabytes. And this is without dependencies. Also, I don't have a bunch of stuff down here, but just to give an idea of the magnitude of what we're talking about, right? And again, developer experience, this has a tax. There's a tax with this, right? There's a ton of binaries you need to move around. Down here, really not that much. Okay, yes, this is the thing. So in the space of WebAssembly, there is an initiative called WebAssembly Component Model. And I've been using the notion of components when I talked about these Spin components as being these small WebAssemblies that implements these functions that handles various parts of my application system here. In the WebAssembly component, that is sort of the same, but a little bit different. Really, what we are, part of what is trying to be solved with the component model is to create a way for WebAssemblies, well, a way for you to compose applications by stitching together various different WebAssembly modules. Now, you saw how the Rust WebAssembly that we built for Spin had that HTTP annotation, and basically that means there's an API contract between that component and our host. What the WebAssembly component model gives you is a standardized way to describe those interfaces across WebAssembly modules, which means that I can build a WebAssembly module where I can say, well, I expect someone to deliver me an HTTP server, or I expect someone to deliver me a key value store. And you can express that in a language called WIT, WebAssembly Interface Type, probably?
Yes.
Yes? Thank you. Okay. So you express that in that language, and then together with your WebAssembly, you can carry that WIT file around, and now anyone can come and implement those functionality and provide them to you. So in the case today where we build components that are compatible with Spin because we sort of have a contract that we've defined, we are working together with other people, amongst others, our former colleagues at Microsoft, in defining that as a standard we call WASI HTTP. So what that is a collection of these WebAssembly interface definitions, which are then called worlds, right? So you have a world that is a combination of things that are being offered when you get into that world, right? And the way that you express how you offer things is by defining exports in the language there, right? So you have things that you can export into that world, and anyone who wants to come and live in that world will then have a definition of certain interfaces they need to import. So that's sort of how that contract, in those WebAssembly interface definition files, you define the imports and exports that are required and that you provide. So what's interesting about that is that in the bytecode format that we compile to from all these different programming languages, we actually now have a way of defining dependencies across them. So I can have So that's actually how we can have a Python component in Spin work with our Spin host that is written in Rust, because we have that WebAssembly contract in between the two. So a way to think about this is, if today you sort of, there is this contract between how you could say how you become a host, or how you become a guest, or how you are operator, or how you're a developer. You have a few options today, right? Either you do something that is low level, which is, you have a container that has some OCI, typically it's Kubernetes, right? We know there's a standard for, in the Open Container Initiative that defines that, but most people use Kubernetes today. So that's sort of like, one way of thinking about the guest host ecosystem, what that looks today. Or you can have a virtual machine, right, which is basically an operating system. Or you have a choice of doing something, that is proprietary if you go for the type of functions and Lambda styles. Well, you have to rely on those things. I do know that there are some open source efforts around serverless frameworks and other things, but they're really not widely spread today. So this is sort of what you are stuck with when you have to think about that. Now, what the WebAssembly component model can enable us to do is that if I, as a developer, write a certain component, and I declare a few dependencies that I have. So the Rust component that I just created needed that HTTP thing because it needed a contract to do HTTP request response models, and it also needs a key value store. Those are the things that I need as my component, right? So my world is defined as I need these two things. Well, there can be someone down here, and it could be the Spin host framework, it could be your implementation, it could be, another cloud provider's implementation, it could be your ops team's implementation, who then implements these and exports the HTTP and that key value thingy, have these two worlds meet, and this is a place where you can go and run your component, right? Where you sort of define that dependency, which is, what we're doing in Spin right now. So Spin offers these things, so any component you write that uses these things will be able to come and be hosted and live in that world. There's a lot more to the component model than this, because some of the interesting stuff is that we can do a lot of static analysis of these components, which means that we can inject various things and extend stuff. One of the scenarios that we typically talk about, is like you can consider if you have some sensitive information that would go into this component, for instance, right? You could actually put a component in here that both imports and exports or the HTTP, sort of as a middle man or whatever you want to call it, that sits here and just scrapes out any sensitive information in the HTTP request. Let's say there's an HTTP request that involves things like credit card or other stuff of things. You can inject that component, you can take that out and make sure that these other components that, that require some of the other information down there does not get the sensitive information. And you can do that without having to change these things, because it's the same interface that this guy is looking for, even though that you add something in the middle here. So these are some of these ideas and things that we're thinking about around the component model, and Spin is going to implement these things, and hopefully, I would say a timeline of three months, this will become more real across tool chains. I tried to build a WebAssembly by linking together components a few months back, and that was very hard. So there's a little bit of work to be done, but eventually we'll get there. You had a question?
Yeah, so how does the component model deal with versioning of components, or is that not part of it?
I don't think that's part of it today, no. The interfaces as such are not versioned.
That seems like a major oversight.
Yeah. No, I don't think so. No.
No, you don't think so? I mean, to a large degree, it's equivalent to dynamic library loading, right?
Yeah, but the thing is that there is a set, and I'm moving somewhat out of my comfort zone here. You can probably see that as I'm start sweating even more now. But what you can define as those interfaces are really just very primitive types, right? So you won't have, you will have function signatures and stuff like that in there, right? So you can always add functions to them if you want to, but you have to deal with that backward compatibility. Yeah. Did that make any sense?
Yeah, I understand.
Okay, good. Thanks. Okay. I think I've used my time now.
Yeah, I think we maybe maximally have room for maybe one quick question.
Okay, yeah. Yes.
What would be like a very good use case of spin compared to container?
Well, I would claim anything. But I think first of all, where we are right now is I think we're very much thinking about this. If you have something that you think about a serverless framework would be nice to use, then definitely this is a good place to start. Like we don't have a proprietary thing. There's some local dev experience. Like this is me. Anyways, we've eliminated cold start. You can use any programming language, yada yada. But I think the last thing here is that I actually think that we can do a lot more than what you would traditionally do in serverless type of applications today because of the persistent storage and because we really haven't found. We're not like that hard battle tested yet, but we haven't found sort of limits in terms of this model of having to load unload in terms of request handling and things like that. So there really shouldn't be anything that should necessarily concern you in that regards. But anything webish, right? Anything that needs some HTTP webhooks that's the easy one, right? A simple function, you add that in and it just sits there. You don't have to think about scaling or anything. You just deploy it to the cloud like my Friday app. Those are really, really good. We actually built a CMS because we could. So all of our websites and documentation sites are running using this. We have one of the components we have in that template list is a file server, static file server. So basically we build a WebAssembly component that acts as a file server, which means you just want to host some files or static files, some websites, whatever it is, you can also do that. And that's basically how we build our CMS. We have the SQL storage, we have the key value store, like we have all those persisting options. To be fair to the whole SDK and programming language story, if you can do Rust, do Rust. Compatibility-wise, it's far ahead of anything else. We do a lot of work together with other companies in getting good JavaScript to WebAssembly compilation, the same with Python to WebAssembly. We just released an awesome blog post yesterday, by the way, about how we've expanded a lot of the Python libraries that you can use in WebAssembly. But Rust is definitely the language that is furthest ahead in terms of that. We have this one. For inspiration, we have something we call the Spin-Up Hub, where you can go and see some of the things that people have built. Developersfermyon.com hub. You'll be able to see a few, some examples and other things down here that you can just get started with if you want to. And there's a Discord channel somewhere. There's the Discord. Oh, one slide I want to show. I want to show this one slide because I know this is a Rust meetup, and I'll be done after this. So I wanted to have a slide which is, why did we use Rust? So I actually asked on Slack, and I think it was just easier to just give you all the replies. So I'll just give you a chance. Can everyone read it, or should I read it? Okay, anyways. So I'm asking, can I get 5 bullets as to why we chose Rust for developing Spin? And I'm calling out Rabo, who's one of our founders. He's the CTO. And I'm saying I need to go to this Rust meetup and tell some things. So he says, point 1, WebAssembly ecosystem has amazing tooling in Rust for running WebAssembly components. Particular Runtime. Runtime is also written in Rust. 2, it's my favorite language when I started the project. So half joking, we also had an implementation of something similar to this in C# back in the Microsoft days. And then 3, memory safety is pretty important. Ryan chimes in. Ryan Levick is probably known to some of you from the Rust. Ryan is also at Fermion today. Ryan says low resource utilization, high performance, and then it offers correct by construction guarantees, which I think he's trying to correct routing. He's talking about memory safety. So Router says replace number 3 with Ryan. Then Joel comes in. Joel Dice is he works a lot in the Bytecode Alliance project. He's done all the Python to WebAssembly work and JavaScript to WebAssembly work. And he said it's just better, so stop asking questions. Router says what Joel says, Router laughs, and Ryan says Ferris is cute. And Router says Ryan is the one who taught us Rust, so we had to. And then Router says we just wanted to avoid having to rewrite it in Rust 6 months later. And we all agreed this was the perfect slide. So that's it.
All right.
Thanks, everyone.
Yeah.